Thank you, everyone. My name is Antonio, and on behalf of the Comets team, I'd like to thank you all very much for being here today to listen to these presentations. So we are going to talk about our work over the past few weeks, linking meteor shower observations with detecting long-period comets using machine learning. So before we get knee deep into the details, I just want to make some quick introductions here. So as I said, my name is Antonio, and I'm joined here by my team, Andres, Susana, and Marcelo. And we also want to make a big shout out to Jack Collison, who was an enormous help in getting much of this work done. So without further ado, let me kind of frame the problem here for you all. So comets, these are dirty snowballs flying around the solar system. They're rocks, they're ice, some other stuff. Most of the time, they're hanging out in the farthest reaches of the solar system. Every now and then, one of these things' orbits will be perturbed such that it comes in the inner reaches of the solar system. Sometimes we can see these, right? Every now and then, some of those can be perturbed and their orbits can actually intersect with that of the Earth. Obviously, an impact of the comet would end very badly for most, if not all of us. So the idea is we want to know when these things are going to happen before they happen, right? And right now, directly detecting these things is kind of difficult. We can really only see them when they're about at the orbit of Jupiter, which only gives us maybe on the order of a year's worth of preparation time. So we want to extend that warning time. And we're going to do that using meteor showers. You may be wondering what that has to do with anything. So the idea here is that meteor showers, they basically result when comets coming close to us, they leave behind a trail of breadcrumbs, right? Their debris traces their orbits. When the Earth smacks into this trail of breadcrumbs, that's what we see as meteor showers. And so by studying those meteor showers, characterizing the orbits from where they came, we can basically characterize their parent bodies and actually try to find these things. So with that, these were our three main objectives for this summer. The first was to improve and automate the identification of meteors in video surveillance surveys of the sky using machine learning. The second was to actually search for meteor shower streams and outbursts in these huge databases of meteor orbital data. And the last one, the key point here, is that we wanted to find rare meteor outbursts that could be related to these long period comets. So with that, I'll pass it off to Marcelo here.
Thank you, Antonio. Hello, guys. Well, let's talk more about long period comets. Well, I'm showing you a diagram and showing a path of long period comet. So you can see on the left, comet, it's near the sun and his surface is hot. It's hit by the solar heating. So the comet started to throw debris, chunks of rocks, chunks of ice rocks. And then you see a red bar, small. Then you go to the middle of the center of the picture. And then when the comet is going away, you see that red bar more growing, narrow and thin, and now this debris are now doing a first revolution, and then you see debris ahead the comet and debris back in the comet. So when the Earth is passing by the debris from this long period comet, for instance, we have a meteor outburst. This is from a hypothesis called wandering trail hypothesis. So this is the base that we are doing our work now. Okay. Well, I'm showing now, let's talk about meteor showers. You see, Perseids meteor showers is a good example of a comet that throw debris. These are meteoroids, and this is the Earth here. When the Earth is passing through those debris, we have a meteor showers, okay? So this is a good example of debris from a comet. Well, how we gonna do this? How we can make meteors registry? So you see from the CAMS project, a box with 16 cameras, and then we put this on the roof, and we have this computers doing night by night analysis from meteors that are registered from the night sky, the meteors coming. So it's a huge effort because up to now we need human intervention. You can imagine day by day getting data from a lot of meteors network all over the world, as America, United States, Brazil, Europe, night by night, getting all those data and make analysis, cleaning data, because you have to separate what is a meteors, what is not a meteors. For example, fireflies, airplanes. So you have a lot of work to do. So this is why we need a new tool, a new way, a new approach how to wrangling this data. This is why we are doing our effort in this program. And then also as well, with this huge data that is we're gathering, we could do this. This is a celestial sphere. This is many points. Each one of these white dots are meteor orbits evaluated. It's 1 day of data. These colors are meteor showers that we have already known, but we have a lot of data that we could do new things. And these are the networks that are getting data to this sphere. This is a web that you can go through and see this already online. Okay, so it's also a citizen science project. It's a citizen science effort to get all those people all over the world, 24 hours, getting meteors data, and then join together in a huge cloud data, meteors cloud data. Now, Antonio.
Okay, so that's the basic idea underlying this whole process, right? So what did we actually do, this summer to improve this process? The first, as I mentioned, was to automate and improve meteor classification. So this is the basic idea, right? So in these surveys, anytime something moves in the sky, the camera picks it up, records it. We get an image, we get a time series. So in this case, this is an example of what a meteor looks like from the CAMS survey. So here we have the trajectory on the left, so it's just X and Y position as a function of time. You can see it's very straight and linear. So that's kind of what we want to look for meteors, right? On the right there, we have what's called the light curve. So this is the brightness as a function of time for this source. And you can see that it has a well-defined trend, right? It has a smooth rise, it peaks, gets fainter. So that's what we want to say is a meteor. On the other hand, this is what we want to filter out. So this is an example of something that is not a meteor, but triggered the detection. Right? So here we have on the left, again, it's this object's trajectory, and as you can see, it does not look nearly as nice and linear and straight as the meteor. It's kind of messy. And on the right there, the light curve is basically just a bunch of noise, right? There's no pattern which is there. So this is the kind of stuff we want to try to figure out how to quantify the differences between the two situations. That's what we did. One way we tried to do this was by actually manually extracting features from these data sets. For instance, things like the straightness of the trajectory, straightness of the line, right? Things describing the light curve, what the average brightness is, what the shape of that light curve is. So we manually extracted these features from 200,000 objects and ran them through a random forest classifier. And it turned out to do pretty well, actually. As you can see, we ended up with a precision of about 90%, meaning 90% of the things that this algorithm said was a meteor was actually a meteor. And a recall of 81%, meaning that 81% of the things that we knew were actually meteors were correctly classified as such. So this thing works pretty well, and it also works pretty fast, right? So 200,000 objects, a human doing this by eye takes weeks, and the computer algorithm did it in a few minutes, right? So that's the power of this method.
So in addition to the method that Antonio just described, we also used a deep learning method called long short-term memory. This is an LSTM network. It's just a type of neural network that can be fed in a time series and projects the time series into a latent space that then encodes the information in the time series. And the power of the method is that we can actually, we do not need to manually extract features from the time series. We can let the algorithm of the neural network actually learn by itself what are the important features. So here we see, we actually fed, so we fed the XY position, time, and intensity of the time series into this algorithm, and then at the end, we fed it into this LSTM network, and at the end we get a prediction of whether the time series corresponds to a meteor or not. Using this method, we obtained a 90% precision and an 89% recall. But on top of the time series, we also used image data. So these cameras are actually collecting images. These are some examples of what the images look like. On the left side, you see some examples of non-meteors. You see lots of clouds. So clouds actually trigger a lot of detections in these cameras. You see planes, you also see birds. And on the right side, you see the meteors. So some of these meteors are very bright, as in this case. Some of them are behind clouds, and some of them are quite faint, so you probably cannot see it, but there's one there. So this is what we wanted to discriminate. We wanted to find, which of these images belong to meteors or not. So for this, we used a convolutional neural network. So convolutional neural networks have been extremely successful at image classification tasks. And we used the standard AlexNet architecture, which we adapted to this data set. And in this case, we had a binary classification in which we fed an image. And we implemented a few convolutional layers followed by max Boolean layers. And at the end, we had 2 fully connected layers. And instead of the 1,000 categories used in the ImageNet classification, we had 2 classes that we wanted to determine either a meteor or not a meteor. In this case, we obtained an 88% precision and 90% recall. Here we compare the 3 methods that we used. So we had images, we had tracklets. For the images, we used convolutional neural networks. For the tracklets, we used a random forest and an LSTM. And we see overall the LSTM obtains the highest F1 score of 89.6, followed closely by a CNN of 89.5. But the significance of this, beyond the numbers, is the fact that every night, meteor astronomers have to process these large amounts of images that come in, or time series that come in, and they might get around 500 time series or 500 different detections, and they had to manually go through these through this data. And now that we have algorithms that can automate this process so that it doesn't have to be manually done, so the data that actually goes through to do the science is actually cleaner. So. Now, yeah.
I'll take it from the things. So the data that is being collected by these camera networks are already producing about 1 million meteors. And as we implement the methods that we have developed in this program, we will be able to collect a lot more in the time to come. And that's going to create this very rich data set of meteor data that will allow us to learn more about the natural history of our solar system. So we already have, as I said, about 1 million meteors that have been identified, and we have orbital parameters for them. And we wanted to see if we could already start extracting some information out of this data. Basically what we did is we took all of our meteors, 1 million of them, and we partitioned them in time of the year. Say we divided the year in octants. And today I'm just going to show the data for one of those octants. At each different time of the year, you get different types of meteor showers. So the first thing that we do is we partition our data. Sorry. Then we reduce the dimensions. And for each meteor that we have multiple parameters that we have collected. Some of them are like physical parameters that describe this meteor, and some of them are directional parameters. So we want to reduce this data to see if we can extract structure that is multidimensional, basically. Once we reduce this structure, we apply clustering algorithms just to see if we can find groups of meteors that are similar to each other. And then we try to validate this data. So in this way, we go from single meteors to meteor showers and potentially to hours. This data here just shows this partition data. We're looking only at the solar longitude period between 90 and 135 degrees. These are about 125,000 meteors. Each of those dots is one meteor. If you just look at on the left-hand side, this panel shows you that there's a little bit of structure. We're looking at time and space. You can see that there's some structure, and these on the right-hand side, those are the meteors that have been assigned to different meteor showers by humans. But just by looking at it, you can't really say that there is a lot of structure. So we wanted to see if we could extract more information out of this data. So now what we did is we took the same data and we started to explore it. The first thing that we did was a principal component analysis, which takes all of the variables and it creates a new set of variables for a data set that are orthogonal to each other, and they are organized based on the amount of variance that is explained from our data. So here on the right-hand side, you can see that there's not a lot of clear structure, similar to the previous plot. On the left-hand side, the variable factor map shows that different parameters contribute to the variance in our data. But this is not a very good way to actually analyze the type of data. So we have to look at different types of dimensional reduction algorithm. For this, we use t-SNEs, T-distributed stochastic neighbor embedding. And what this does, and again, each of these points is one meteor. What this algorithm does is it takes points in multidimensional space and it projects them in a 2D space so that we can understand it, and it groups data points based on similarities in multidimensional space. And what you can see now is that the structure that was previously hidden from us is starting to reveal itself. You see different clusters, and those clusters are groups of meteors that have similar orbital parameters. We wanted to validate if we could identify known established meteor showers from this data using this approach. Remember that the clustering, or this multidimensional scaling procedure, did not include the labels for organizing itself. And one thing that you can see is that different clusters, here I'm just projecting one of those variables. This is the angle that the meteor enters Earth. And you can see that different clusters have different angles. So we're finding structure that is real, right? And we have these for all of the parameters that we have. But then what I did is I projected the known assigned established meteor showers. And what we can see is that this algorithm correctly clusters the known, these are the top 5 meteor showers. And these green ones here, those are the parasites. That's the data that Marcelo showed in that plot in which you saw the comet debris going around planet Earth. So we know that, for example, these meteor shower and all of these guys intersect Earth's orbit. That's why you have also a potential for collision with comets, right? Then we wanted to see if we could then identify new clusters. And for that, what we did is we took our data set and we clustered the DB-scan, which is a density-based spatial clustering algorithm. What it does is it takes points, again in multidimensional space, and it will cluster them based on density. And it will separate different clusters based on areas of low density. And what we see again is that we identified the previously identified meteor showers, but in addition, we find several new independent clusters that were previously completely invisible for us. Because you have a human looking at 3 dimensions, you have a computer looking at all of the dimensions. So each of these new dots or clusters potentially belong to a new meteor shower. So now we have somewhere to look into. We have an idea that we're picking up the right stuff because when we project those known clusters are still revealed. And we also wanted to look at potential outbursts. Outbursts are important because these are the ones that we believe could be informative for us detecting long period comets. And an outburst, again, is a high density of meteors that occurs in a very short amount of time and space. Okay, so using our similar procedure, we identified several clusters that have those characteristics, right? And some of them are embedded in larger meteor showers, meaning that they probably come from the same direction. Some of them are independent, which is very interesting. But basically, we're able to find groups of meteors that have that signature. This doesn't mean that each of those points is a long period comet that is going to come and hit us. But one of them could be, right? And what we do, this allows us to generate an orbit, to predict an orbit for that long period comet. And that's what we would look into. The astronomers would take the data and then do a dedicated search based on those orbits that we identified. And so our study basically has developed a way to automatically identify images from meteors, from non-meteors, from image data. And our performance is already above or approaching human level. We can also recover known and unknown meteor showers. And finally, we're able to identify those outbursts. And that's the important point that we want to stress, besides the new meteor strings. That's again where we would look for those long period comets. And so this study again gives us just a window into the complexity of our universe and the beauty of it, and how much information we can extract from the work that we do just by doing these type of citizen science. And with that, I just want to conclude and thank everyone in the program, and NASA, IBM, and NVIDIA, SETI, and the FDL. So we'll take some questions.
How about a round of applause? So the format is, what we're going to do is we're just going to go to our reviewers. If you could speak for just a little bit, your first thoughts, initial ideas, or kind of, I guess, directions for future investigation. Perhaps Pete or Jesse would be.
Well, I used to do some work on this, but I was pretty skeptical. Yeah. I'm kind of, I don't even know if I can listen. I'll speak for it. I'm pretty skeptical of that last chart because you picked out a couple little things that look like noise to me, and others you didn't. So, I mean, I'd be more convinced if you actually had some other data that seems to validate them, like known or unknown meteor storms picked up.
So basically what we do is I separated the plots, but it's all found in the same clustering run. So it identified at the same simultaneously the small and the large clusters. The only validation that we have right now is that the large clusters were known data. We can't validate any known data until somebody finds them. But I totally agree with you. This is a step forward, and it needs to be validated. So
yeah, there needs to be some error bars on it. I guess that's what my point is. That's an interesting plot, and there's a couple little pieces that look like noise on it that you picked out. So
basically, what this scan does, it also allows, what it does, it excludes noise data. So the noise data points are actually, which are basically different than the others because they have low density. Those points were not clustered. Yeah.
Excellent. Thanks, Pete. Jiyong, no.
So you had a great presentation, and also the fact that I've met you guys before, so I kind of know the project well. I'm not well, but at least I have a brief idea. I'm not a planetary scientist, so this is more like machine learning stuff. But so I have a question regarding picking the best model for the meteor shower classification. So the first two models, the LTSM and random forest, used trackles, right?
Yes.
And CNN used images, and I think it could be kind of unfair to compare two models because they are using different data sets basically. So yeah, so that was one thing I was concerned about picking the best model for each classification. But other than that, I think it was really a great project. Good, thank you. Thank you. Good.
So I guess not over on this slide, you have about 10% of false positives, if I interpret this correctly. So we have a saying at NASA, which we use a lot, which is treasure your anomalies, because you can learn a lot from those 10%. So the question I have is, what are those 10%? What sort of detections are they? And do you think you can learn this to improve your algorithm?
Yeah, so we looked at the wrong predictions, so the false positives and false negatives. So what happens is that a lot of the meteors that are being missed by the network are really, really faint. So I guess, yeah, the network kind of misses them. Because it's actually difficult to the human eye to see them. I went over like these images, and it's also hard for me to see the meteors sometimes because they're so faint. So this is one error, and there are also other sources of error. For example, we think the data annotation itself, there's errors there as well. Some things also look a lot like a meteor, but they're not a meteor. So the network sometimes gets confused there. I have some examples of the false positives and false negatives, but I couldn't show them, but I can show you later what the errors are. But yes, we have looked into what the errors are, and we think that one, perhaps actually cropping the image around the detection point might help. So instead of feeding the whole image, just feeding a crop, and that might help because then it's actually more localized. What's one thing. And the other thing is actually cleaning up the annotation. So we had 2 humans annotating the data that we had, but this could be a much larger effort where we actually make sure that annotations are more accurate, and therefore the network hopefully will learn better. So.
Ian.
As a machine learning person, I don't know a lot about comets, and I immediately start thinking about what kind of information we can get in the meteor showers. I was wondering if you know what percentage of comets are actually traveling in a way that their meteors arrive on Earth where we can see them. I was also thinking maybe one factor that could make the meteors more interesting to us is that possibly comets that are more likely to strike Earth in the future are also more likely to send meteors our way. Have you done any kind of probabilistic modeling to estimate what percentage of comets that are dangerous to Earth end up sending us these meteor showers?
Right. So I don't know. I'd forward that to the experts on meteor astronomy.
Or perhaps something to use.
In fact, we have a probability of 1 in 60 million years to a big comet, kilometer size, to hit Earth. But we have also on our surface, Earth's surface, more or less between 5–10% of the big craters, maybe 50 kilometers, 10 to 50 kilometers are from long period comets. More than 10 craters on Earth.
So I guess what I'm asking is, if we know that there's a long period comet out there, how likely is it that the meteor showers coming out of the debris from the comet will be observable in our atmosphere before the comet hits us?
Okay, so this is why we are trying to find out meteors outbursts. Meteors outbursts, it's exactly the phenomena that we're trying to find out, because they are kind of signal that a long period comet could be arriving in few years, for example. We had an example a few weeks ago with the Borisov comet. It's a long period comet, And with using this hypothesis, it was evaluated that we would have an outburst, I think it was in the 29th, 30th July. And in fact, we observed, using video monitoring lunar impact, we observed a lot of impacts on lunar surface in the exactly moment of the peak. Okay, this is the way.
Great, thank you. Victoria.
Thank you very much. This was a really good start on tackling a critical problem. We know a lot about comets, but we're not quite sure where they all are. So thank you. I appreciate that. My next question is, of the work you've done to date, what we would hope to do is that it would be brought forward and would be implemented, okay? And you could use it in academia, citizen science, whatever. So what's the prime problem to tackle next in order to start to move forward to that goal?
So as far as moving this forward and implementing this, yeah, I mean, I think we need to work to implement these models right now. We were thinking some kind of ensemble, averaging the predictions, better classify meteors so we can clean up these large databases. But I think as far as, actually classifying the outbursts, I think that the validation is probably, validating the clustering and, making sure that we can actually observe these things when they happen. It's probably the biggest thing.
Thank you. Jesse.
Actually, to follow up on that, of course, not all meteors come from comets, right? They can come from asteroids. And how are you going to differentiate, and how are you actually going to validate that your clustering is correct?
So you're completely right. Meteors come from different sources. The idea for the long period comets is to concentrate on the outwards, those concentrated groups of meteors, and not all of them are going to be from long period comets. The best thing that we can do right now, because we can see them, is to learn from those predicted orbits and look into those orbits and see if we can see something. We're reducing the space in which we need to look for. Right now we have nothing, right? Whereas if we do this, at least we have 50 places to look into. That would be the first thing. In terms of the meteor showers, I think that because some of them are periodic, we should be able to validate those pretty easily, just by expecting what they're going to reappear in the following years.
So are you pulling orbits out of your clusters at this point, or is that a next step?
That's the next step, exactly. So from each of these clusters, we can produce an orbit. Yeah.
Excellent. Well, thanks so much, everybody. We give you a round of applause. Go and have a drink, relax.